One is we are going to complete the model selection part. That is one. And then what we are going to do is we are also going to start with the ensemble learning process, right? We are going to start with the ensemble learning process. So these are the two agenda that we have for the day, right? Okay. So as I said that you might, I'll just probably start from this bias and variance part once again, right? So, so the question is bias and variance is as important as underfitting and overfitting the model to analyze their correction. See, those are two sides of the same coin, right? If you talk about bias and variance and underfitting and overfitting, it is two sides of the same coin, right? So, which means that if your model is a biased model, then probably it's an underfit model. While if the model is having a high variance, yeah, it is a overfit model, right? So both of them they are related in some way or the other, the bias and variance part, right? As I said, Subramania, just probably try to keep the question, right? I'll just wait for you to respond in the Q&A part. Put the question in the Q&A section, right? I'll respond there. So that will remain as an answer with you also, as well as with your friends also, right? Please put the question in the Q&A part and let me put across the response for the same. Put the question in the Q&A part. The same question you can put in the Q&A part, right? Also tell me something. When is your last this thing's schedule? Your last IA. When is that schedule? When is the last IA schedule? Okay. So tomorrow morning is the last piece. Okay. So let me answer this question. So bias is related to overfitting and variance. Sorry, bias is related to underfitting. My bad. And variance is related to overfitting. Biased model is usually underfit model, while model with a high variance is usually overfit. To see what it means is that if you have a biased model, right? If you have a biased model, that is definitely an underfit model. But an underfit model doesn't necessarily lead to some kind of a bias. Similarly, a model with a high variance, a model with a high variance is usually a overfit model, right? But a overfit model, whether it will always result into high variance or not, so that is also something which needs to be analyzed, right? Okay, so this was the part And okay, today I is there in the evening. I in the evening today. Okay. So this was what we were doing in the last session, Subramanya. Right? If you see, so one is a model with the high bias, right? And the on the this thing on the X coordinate, you have model with high bias and low bias, and on the Y coordinate, you have things with low variance and high variance. Now, what it happens, right? So if you see the case of a model with the high bias, so a model which is having a high bias. So high bias means that typically it has created a very simplistic assumption about the model, right? So let's say for whatever value of the model, right, for whatever features, if you are giving some kind of a constant answer, right, right, whatever parameters are there, you are giving some kind of a constant answer for the same, right? You see out here, the answer is very consistent. So the answer is very consistent, right? And in generally, it is wrong, right? Answer is consistent and it is wrong. Then what will happen is that bias is high because the answer is wrong, always wrong. On an average, there is a lot amount of errors. But on the variance part, since it's the same answer that you're giving, right? Same answer that you're giving, right? So the variance is low, right? So here's variability. In this particular case, right? This is probably the worst kind of a scenario where your model is having a high bias as well as a high variance. You see out here. So such so all these are the bias parts. So bias is also high, and the variance factor that is also not consistent. That is also pretty inconsistent. So high bias, low this thing, high variance, high bias, then low variance. So and the other one is this one. So this one you see, like the previous one, it is not that much bias. While saying things that see you have made such an assumption about the model that always the answer is lying in this particular side, right? So the bias is high, as well as on the variance part, the variability part, you can see that that is also on the higher side. While the one on this one, so let's name it 1, 2, 3, and this 4. So C part is where the bias is low. In that way, it is good, right? It is not biased in a particular fashion, but the variance is high. So this one is high bias and high variance, high bias and high variance, high bias, high variance, and this is a low bias and high variance. So this is the idealistic model where the bias is also low. So this is your target, actual target, and this is where your answer is generally scattered around, and the variance part is also low. So for high bias model, underfit, high bias, underfit, and low high variance. High variance. This is the scenario which comes up, right? Okay. So do you have any further follow-up questions on this, Subramanya? Further follow-up questions on this particular bias variance? I think you had some more queries. No, very good. Okay. So what I'll do is also at the same point in time, I'm also going to put you on the unmute part so that allow to talk, so that you are also able to discuss your. So, okay. Let's come to the notion of overfitting. So overfitting, you'll find that initially, right? Initially, this particular part. is the error is very high. So you see the error is high consistently on the training as well as on the testing data or the validation data. So it's an underfit model, right? In this particular section, it is a underfitting zone, right? Underfitting zone where what happens is that the error is high and the error is consistently high on both the parts. Error is consistently high on both the parts, right? Okay. Move to this one. This is the out here from an underfitting zone. It moves to a overfitting zone. From the underfitting area, it moves to the overfitting. And one of the hallmark of that is that see the performance keeps on widening. If you see that here the performance somehow it starts diverging, right? So while the error on the training it while it dives, the error on the testing or the validation it goes up, right? This is what happens. So out here, you see out here, you see that the performance between the training and the validation that is still comparable. But we see out here that it tries to probably diverge, right? So if I see overall, if you see, I think around this particular zone is where the error, right? You see this particular area. This particular area is when your complexity is also on the lower side and your error is also on the lower side. Beyond this, if error shoots up, right? See, at this point in time, if I see compared here, so here the training error is very low. Training error is very low. But if you see here, the difference in error becomes high, right? So high difference, right? While here, the part where I have specified, so here this one is a very low difference, right? And this one is also a very low difference, low, right? And then it starts increasing. So we can say that, Professor, what we can do is we can have, let's say, a model where it is very low. So out here, so here, both of them, they are comparable. Out here, both are comparable. Isn't it? Both are comparable. But the problem is that here, right, your error rate is still on the higher side. So this is the difference in the error, right? And it is quite on the higher side. While out here, if I see out here, if I put so here, this is the error, and here probably this is the error. So on the lower side, the error is on the lower side, and the difference also on the lower side. Right? That is what happens, right? Okay. And then we have discussed this particular diagram also. This is an underfit model. This is an overfit model. And how do you know the underfit part and the overfit part? If you see out here, right, in this part, right, it's an underfit model and it is consistently underfit. So if the data, underlying data changes, right, so this is misclassified, this is misclassified, this is misclassified, right? I have drawn a very simplistic model, right? This makes this thing misclassified. If more and more data point comes in. So for example, a new data point has come in out here. One new data point has come in here. A new data point has come in here, here, right? And then probably this one is also a new data point. And then out here, this is a new data point. Right? So your underfit model is still unphased, right? It is not too much bothered, right? So new data point has come in, right? It still doesn't it doesn't have to make any change. So whatever it was earlier, also it was giving high bias. Now also the bias is high. Whereas see for the case of the overfit model, for the case of this overfit model, the bias is low. Overfit, low bias, right? It has been able to accommodate for all the this thing. This one are the gray and this white points. This have probably been able to distinguish both of them properly, the gray and the white. Now, if some more point comes in, if some more point comes in, see some more point has come in, right? Then this entire model is going bad. It has to readjust itself, right? Realign, readjust itself to probably adjust to the needs of this new model new requirements, right? So that is what has happened, right? So to summarize, model with high bias usually underfills the data and makes simplistic assumption, and model with a high variance generally overfills the data and learns too much from it. So a good model is where you need to have some kind of a balance between the bias and the variance. Right? This is where probably both of them they will be almost at par. Right? Okay. And then we discussed these three diagrams, right? Overfitting, underfitting, and a good balance. Okay. And then we came to the feature selection part, right? So we understood that if you have too many features and the data points are not very high, what might happen is that your data point they might overfit, right? It might end up into overfitting because you are not having too many this thing, too many data to learn, right? So that's the problem. So more features, less instance of the data will become highly overfilled. And what this Occam's razor says is that your model should be simple and explainable. With too many features, what happens is that the explainability part of the model gets lost, right? And if you have a lot of irrelevant data, it will put the noise in the model, and we want to reduce this noise as far as possible, right? So this is what it is. So feature selection, right? So what we do for feature selection is that we select a subset of the relevant features for processing without any transformation. Subset of the relevant features we select without any transformation, right? It is also known as attribute selection or variable selection. Attribute selection or variable. That is the feature selection part, right? So here, no transformation, uh, right? And a good subset, right? This is what we do, right? And if you're able to find out good features, what will happen is that the learning of your model, the knowledge of the model, that will increase significantly, right? So I gave you this example yesterday that if you have a little amount of time and if you have to learn about the model, right? Then what will happen is that this irrelevant garbage data you can discard, right? You can focus more on things which makes much better sense, and the process it can help improve the model accuracy, right? And also, like if you're having lower amount of variables, reduced amount of variables, what happens is that the time taken to train the model, that also becomes significantly lower. So if you're having categorical data, chi-square test is one of the feature selection method for continuous. You have this Pearson correlation, right? And these are some of the feature selection strategies. So what you have is the filter method, the wrapper method, the embedded method, as well as this hybrid method. So these are some of the strategies. I have discussed all these processes, right? Filter method is where even before you put the data to the model process, we try to select the best subset. And then once the best subset is selected, we put it to the learning algorithm. In terms of the process of feature selection, right? This process is a pretty fast process, right? This process is a pretty fast process, but sometimes quite time taking, this feature selection, right? So that is one. And these are some of the examples: information gain, Pearson correlation, chi-square test, right? Linear discriminant analysis, LDA, right? So that was the filter method. Then you have something called as a wrapper method, right? So for the wrapper method, what happens is that you put this model to the set of all the features, and then it selects the best subset, right? So what happens is that in the wrapper method part, a continuous cycling process it happens, right? A cycling process, and it tries to probably select the best from the heap. So this one is computationally very expensive. Computationally very expensive because what happens is that within the modeling process itself, it tries to select the best possible features, right? So these are some of the methods. RFE, forward selection, backward selection. These are some of the methods which are out there. So typically what happens is that these are computationally very expensive, right? So in the previous case, on the computation part, it was probably not that much intensive, but this one is computationally very intensive, right? So this filter method, you'll find that they will use really some kind of a statistical method for evaluation of a subset, while the wrapper method uses some bit of this cross validation. Now, what exactly is cross validation? Obviously, I'll come to that, right? But in the process, what happens is that the wrapper method computationally it becomes very inefficient, right? So filter method, many a times it fails to find out the best possible subset of the features, but a wrapper method in general, right, it will provide the best subset of the features, right? So wrapper method will provide the best subset of the features, right? Okay, and then you have the embedded method, which are probably a much more evolved method. So this method, see the problem with these methods, right? See, for example, with the filter method. Filter method, if you look into the model explainability part, it is quite a bit explainable. Wrapper method, yeah, you lose probably a bit of the explanatory part as to why you select a particular subset of the feature over the other. But still, the explainability part is still there. For embedded method, what happens is that the explainability, right, it further goes in probably in a bit tangential or difficult direction, right? So these are some of the methods, right? Lasso regression, ridge, right? Elastic net regression and automatic relevance determination regression, right? So these none of these methods they are part of your syllabus, right? In even the advanced machine learning, right? But again, these are probably the techniques which people uses these days. And I think this is the last topic that we had covered in the last class, which is this imbalanced data set. What you do with the imbalanced data set, I told you that either you do oversampling, so minority classes, over sample, or the majority class undersample. So you oversample the majority, undersample the minority majority class and oversample the minority class, right? So in the process of undersampling, what happens is that from the majority class, you select random subsets. While for the minority class, what happens is you are trying to basically put this class on the higher pedestal. You do a oversampling. So here you do a sampling with replacement, which means the same points it comes uh, and it gets repeated in the oversampled cases, right? So that brings us to one of the very important topics, right? Very important for your evaluation, for your exams, and even for your life, which is this cross validation. Cross validation, very, very important topic, right? So cross validation, what happens is that it is basically nothing but a resampling technique. It's a resampling technique. And here in this process of cross sampling, what you do is that you ensure, right? It's not ensuring, it is ensuring, right? It's ensuring, not ensuring. Ensuring that the results which are uncovered are generalizable, right? So you have some resampling technique, right? And you uncover some results. And what you're trying to do is that you're trying to see that the results that are uncovered, they are generalizable, right, for an unseen data set, right? Okay. Now, Subramania, Sachin has come in. No, not yet. Subramania, my question to you, right? So that you are going to the using contents, right? What is the most commonly used method for cross validation? Most commonly used method for cross validation?
It is k-fold cross-validation method.
Not really. Not really. Not really. So the most commonly used method is called the fold out method or two-fold cross validation, right? So in the hold up method, what happens is that you do a validation where one is the training data and the other is the test data. Right? One you have the training data set and the other you have the test data set, right? So what happens in this particular case is that here the partitions, by the way, are not of the same size. Partitions are of different size. The partitions are of not same size. Partitions are of different size. Right. The data is partitioned into two parts. Right. One is the training and the other is the test. Where again, see, again, it is not usually written in the stone that okay, you can't have partitions of the same size. You can actually have partitions of the same size. So 52 partitions also you can have, right? Where your 50% of the data is for training and 50% data is for the testing. So that is also highly possible, but generally that's not a practice that we use. Right? That's not a practice that we use. So what we do is that the data is partitioned in two parts, right? One is this training and the other is this test, right? And what we do out here is that on the training data, we build the model, and on the testing or the validation data, we test for this particular model, right? So this is what happens, right? If you see, if you're having low number of examples, right? If you see low number of examples, the one on the red, right? If you see the one on the red part, that is my training score, and the one on the green is the validation score. So initially, let's say that I have very small number of training examples. Number of training examples are small, and then I see that on the training data, my score is pretty high. I think this is close to 94%. While on the validation data, on the test data, the score is low. What do you think might have happened? What do you think might have happened in this case? What do you think might have happened in this particular case? What do you think might have happened in this particular case?
Is the error is more in both the cases.
The error is more for which one?
Uh, the training score.
Correct. So score is the score. Score is basically the performance, right? So on the training score, we find that the training score is 95%, while the validation score is 75%. 95, 75, right? If I see the performance sorry, my bad. On the training data, performance is pretty good, actually, isn't it? The performance is good on the training data, while on the validation data, the performance is on the lower side. On the validation data, the performance is on the lower side, right? So that happens for your this thing, for your what they will say for these cases where the number of training examples are low. Now you tell me what happens on the other part where you are increasing the number of training examples. When you're increasing the number of training examples, what happens in that particular case? We increase the
Uh,
number of training examples.
both the training and validation scores uh, the gap will be less.
The gap becomes less, right? So again, so what does it signify? What you said is perfectly correct. The gap becomes less. So what does it mean at the end of the day?
It means we can get the ideal or uh, good model.
Uh-huh. So what happened earlier and how things changed now? What happened earlier and how things have changed? What happened earlier and how things have changed? What you're saying is perfectly correct, right? I'm with you. I'm with you on this, right? But again, my question is that what has changed, right? As and when you increase the number of examples, what has changed?
By increase the number of trainings, there is a
Uh-huh,
chance of uh, sampling in the random samples
uh-huh.
selection.
Not exactly correct. Not exactly correct. See, if you're having lower number of, see, if you see, as and when you increase the training examples, you see the training score goes down. The training score went down. Have you seen that?
Yes,
Right? So I'm putting the model through more and more training. So then ideally the training score should go further up, isn't it? The training
yes,
score should
yes.
go further up, but that is not happening. The training score
But the
has
validation is getting means accurate when the number of
the
trainings are
validation is getting
increased.
accurate. The validation is getting accurate, right? You are correct on that particular part. So what do you think has happened? What do you think has happened? Why is it that for the trading the performance goes down, while for the validation the performance comes up? What do you think has happened? So initially, my performance on the this thing on the training, it is pretty high, and then what is happening is that this performance comes down. This performance all of a sudden it comes down. What probably has happened? What
Actually,
probably?
because initially the number of training examples were less.
Uh-huh.
By that, when the increase in the training examples,
Uh-huh.
that we considered the previous learnings are as a lessons for us to uh, make the validation that benefited.
Not really, not really. I'll tell you what has happened. See, if you're having, if you remember, I told you that if you're having lesser probably instance of the data for training, then what happens invariably is that the data, right, it might overfit the model. So here you are having very less instances, right? The very fact that less instances are there, what will happen is that it is not having too much of a information to probably this thing to get itself trained on. And if it's not having too much of information to get itself trained, what is happening is that end of the day, it is ending up with a overfit model, right? An overfit model generally what happens is that the performance is that the on the training data, the overfit model does a very good job on the training data, while on the validation data, right, or the validation or the testing data, the model will do badly. And this is what is exactly happening. This is what is exactly happening. It is doing a good job on the training piece, but it is doing a bad job, right? A pretty bad job on the the validation data. But then what you did was you increased the number of examples for training, right? You gave more and more instances of the data so that the model can get trained on, right? So if you can have uh, more and more data to train, then what will happen is that from the overfit part, the model will probably come to the part that where it will try to once again learn properly on the data. Not like earlier where the learning was on a pretty lower side. Now the learning will probably it will get readjusted, and this time what will happen is that you'll find that it is trying to do a better job in the learning process, right? That is what is happening with respect to the data that you see, right? So here initially my learning is the overfit case, and then slowly from a overfit case, what we see is that with more and more training examples, it learns well, right? The variable which are important, those things are sorted out in a better way. And at the end of the day, you see that the performance almost becomes at par, which is probably what we require. Understood?
Yes,
Okay. So the first example of this validation technique is this thing called this hold out method, so which is the simplest evaluation method and is widely used in machine learning projects. So entire data set is divided into two sets, which is the training and the test, as I told you. And typically, the data set can be divided into 70-30, 60-40, 70-25, 80-20, or even 50-50, depending on the use case, right? But generally, as a general rule, right, it is not that, okay, this is always applicable. Proportion of training data is larger than the test data. It is a general rule. So what you do is that it gets this thing trained on the training data, while on the test data, it tests itself. So my question to you, Subramania, is that what do you think are the advantages of this method? The method that you see out here, what do you find are the advantages of this particular method? What do you think? What are the advantages of this particular method? Advantages. Advantages of this particular method. What do you think is the advantages of this particular method?
Mm,
Advantages of this particular method. What is your take on this?
The advantages are it is very simple
It is simple.
because
Good. It is simple. Yes, I'm with you
yes,
on that. And
mm, and the advantage is already here. It is there as it can be used for the large set of data.
large set of data. How I mean this particular point, interesting point that you have put up. How it can be used for large set of data?
Uh, by dividing the data,
Mhm.
uh, dividing the training data set separate and testing data set separate.
Okay. Okay.
Uh,
No, you mentioned a very interesting point, right? If you can just justify the interesting point that it is good on that large data set, right? What exactly is meant by the thing? It is correct, but again, I want your justification. What you said is correct, right? That's the reason why I'm looking at how did you justify this one. Okay, so I'll come to that. What are the disadvantages? Disadvantages. That's the advantage part. Disadvantages. Disadvantages. Any disadvantage that you see in this particular method?
mm, mm, entire data set into mm, means entire data set into two means it will not uh, provide individual means as a whole as it divides the data set into two two
Uh-huh.
sets. One
Uh-huh.
is training and one is testing.
Point is not making that sense. Can be a little more specific,
Uh, Simple is as the advantage is useful for the larger data set.
right?
The opposite is it is not much useful for the small data sets. Simple it is.
No, no, no. That is not a good way of looking at it. So the disadvantage, see the advantage, as you said, that it is very fast, right? So when you said large data set, so large data set, obviously, you need algorithms. If you have systems which are slower systems, so large, as and when the system becomes large, the performance of the algorithms that will also suffer considerably, right? So that's why what we do is that on a large data set, right? On large data set, if we have this paid test, it's very simple. I make one split, right? One hand goes for the training, the other hand goes for testing. Right? One hand goes for the training, the other hand goes for testing. Very simple, right? But if the data set size that is on the smaller part, the data set is on the smaller this thing, smaller part, or even if the data set is having a high amount of variability. So what happens is that since you are doing some random division, right? So there might be some data point in the test data which is very different from the training data. And as I've told you that your model is as good as the data on which it has got trained. The model is as good as the data on which it has got trained. And now you're finding that your training data is your test data is probably consisting of examples which were never seen on the training data. So in those instances, the model will fail. What is the disadvantage? Right? This random partition is leading to that disadvantage which I just spoke about. Understood? Understood,
Yes,
Subramania?
sir.
Okay.
Yes, sir.
So that is the disadvantage since the split is random. The training and the validation data subset might differ in both the structure as well as the quality. Right? So what we try to do is that ideally you should try to partition into two by performing some kind of a graphical or statistical comparison with the features. That is probably something that we should try to do. Right? So that brings me to some very interesting cross-validation technique, which is called the LOOCV, or leave one out cross-validation. LOOCV, leave one out cross-validation. So this particular method, you divide the data into two sets, train and test. What with a twist, right? So the twist is that, so let me give you an example. So let's say you have 100 data points, 100 data points, right? So what I do is that I divide the data point into two parts. One part is containing 0 to 99, and the other part is containing the 100, right? So what I do is that I train my model on this data point number 1 to, so not 0 to 99, 1 to 99. So 99 data points I use for training, and this 100 I use for testing. And then once again, I use 1 to 98 and the 100 data point for training and the 99 data point for testing. In the next iteration, I use 1 to 97 and then 99 to 100 for training, 98 for testing. In the next case, I use 1 to 96 and then 97 to, sorry, 98 to 100 for training and 97 for testing. Like so on. So in one case, I use 1 to 49 and then 51 to 100 for training and the 50 for testing. So what I do is that for each of the cases, right, for each of the cases, I use all but one of the data points for doing the training, all but one, except one, all the other data points are used for training, and this one particular point is being used for testing, right? That is what I generally do, right? So then what are the advantages and disadvantages? Subramania, what do you think are the advantages and disadvantages? Understood the method, right?
Yes, sir. Actually, that is from this method, as uh, it will take the entire data. So
Uh-huh.
uh, it will be like there will not be a overfitting. It will be lesser underfitting in the data.
Very good, right? That's a wonderful point which you have put up, right? Since more data point I have accommodated, right? The chances of this kind of model getting overfit is lesser. Very good, right? What else? What else?
Second is this method will look the entire data into as a single uh, data set rather dividing it to two.
Sorry, I did not get this particular point. Come back once again. Come back.
This method looks the entire data set as a one or a single instead of
Uh-huh.
dividing it into two.
No, it is dividing it into two, right? It is dividing into two. Only thing which is happening is that this in this partitions which we spoke about, only one of the partition is being the partition, right, which is being used for training, right? That particular partition has all but one point, and the other partition also has all the other points.
Mm, I think. Sir, one more is uh, we can rely more on the accuracy part also as it uh, touches every means the smallest part in the data as it like 1 to 98, 1 to 97, then 1 to 96,
Uh-huh.
like that. It
Okay, so I'll tell you the advantage. The advantage part which you said was perfectly correct, right? It is exposing more amount of the data for doing the training. So we are essentially trying to probably restrict the scope where the model might become overfit, right? More data. That is a good thing that we are doing. So you are basically helping the model to learn better, right? And then what happens is that at every point in time, I use all n minus one data point for training and only one data point for testing, right? So I'm able to check for the performance, right? Iteratively on each of these data points. So at every point in time, right, I'm having an unbiased selection of 99 points for training and this 1 point for testing. And I'm also trying to give the result on this one lone data point, that what is the performance which is coming. So at the end of the day, what I do is that I average out the performances and see that what is the best performance which I get, right? So this is the good part of the model, right? The bad part of the model is that, see, at the end of the day, you are averaging out the result for 100 partitions, right? If you had 100 data, so you have created 100 different subsets. For 100 different subsets, you are finding out the performance. It might so happen that on some of the pieces, right, there are some data points where which and those data points might be outlier as well, right? It might be outlier as well. The performance completely went for a toss on those particular data points, right? It completely went for a toss in those particular data points, but yet what I did was I averaged out the performance, and in the averaging process, it never caught the attention. Right? During the averaging process, it seemed that all was fine. Right? So that is one disadvantage. Right? So scenarios like this might increase the variance of the model, the variability of the model. It might increase in this particular case. So here you see that the here I'm not creating overfit model, right? I'm not creating overfit model. I'm trying not trying to create underfit model. I'm trying to create a balanced model itself. But sometimes variability might come in spite of whatever checks which you have. The other thing is the complexity, right? So for 100 data points, right, you are creating 100 models. So which means that you are having 1 million data points. Then 1 million times you are creating this model, isn't it? Because at every point in time, n minus 1 points will be used for training, and this 1 point will be used for validation, right? So then what's the pitfall then? Now I've given you enough data point. What's the pitfall then? What is the pitfall? What is the pitfall? Yeah.
Mm,
The pitfall, as you can understand from out here, is that computationally very complicated, right? If you're having, let's say, 1 million data, 1 million records, so 1 million times you are doing the process of model creation, 1 million times. And every time you are having close to 1 million data points on which the modeling process will happen. So for small amount of data, though this is possible, it becomes almost infeasible for a large amount of data. Out of question for large amount of data, isn't it?
yes, sir. And also, it is more time consuming.
It is more time consuming. Definitely, it is more time consuming. No doubt about the same. No doubt about the fact that it will be much more time consuming. Right? So that those are the disadvantages of this is the LOOCV, right? So very high computation, right? So LOCB generally what has is that the variance sometimes it ends up being very high, right? Because of this averaging process, right? So now we saw that the holdout method or the train test has its own disadvantages. The LOCB we try to improve on the disadvantages of the holdout method, but that also has certain disadvantages. So that brings us to this k-fold cross validation, right? So what happens is that in k-fold cross validation, original data is partitioned into k independent and similar subset. K independent and similar subset. And then k models are being built using the data from k minus 1 subsets. And we use the k subset as the test data. Right? And then these results, they are combined using this averaging of the voting. So what it means is that, so earlier in the LOOCV case, we had, let's say, 100 data point, right? So where 99 we are using for training and 1 we are using for testing. In the k-fold case, so we partition the data into k independent and similar subsets. So let's say that we partition the data into 10 independent subsets. So 10 independent subset, which means that each of the subsets are having 10 data points, independent as well as similar subsets, right? Similar subsets. So 10 independent subsets, if I create, each of the subsets, they are having 10 points, 10 points each. So at any point in time, 9 of those subsets, so 9 of those subsets means 9 into 10 data points per subset, that is 90 will be used for training and the rest 10 will be used for validation of testing. So 90 for training and the rest 10 for testing. That is so how many times this process will happen, Romania? How many times this process will get repeated?
10 times.
10 times. Very good. 10 times. So earlier for LOCB, for 100 data points, I was repeating this process for 100 times. And here for the k-fold cross validation, where I have set k as 10, this process becomes repeated for only 10 times. So let's say now my number of points from 100, let's say it becomes 1 million. So 1 million. So or let's say 10 million. 10 million. In the LOCB cases, I probably would have ended up creating 10 million number of training instances, and then I'm doing validation on that one data point for each of those 10 million cases. In the k-fold cross validation, k-fold cross validation, let's say I'm using k equal to 10. If I use t equal to 10, how many times the process gets repeated? Once again, Subramania.
For this 10 times.
Once again for 10 times, correct? So at every point in time, what will happen is that 9 million records for training and 1 million for testing. That is what is going to happen. Even if the data set becomes large, right? For the case of my this thing, this what was the name? The LOCP, right? The complexity increased significantly. Not here, not in this particular case, right? So this is what probably happens. So let's say this is P1, P2, P3, P4, P5, P1, this is P2, P3, P4. So at every point in time, what happens is that in the first case, P2, P3, P4, and P5, those are being used for training, and P1 is being used for testing. In the next case, what happens is that let's say P1, P2, P3, P4, P5. So P1, P2, P4, P5 is being used for training, and P3 is used for testing. In the other case, P1, P2, P3, P4 is being used for training, and P5 is being used for testing. Right? So here, five-fold cross validation has been used. So 5 times the modeling process happens, and then on the unseen data, they are prepared, they are tested, and then we average out the performances. Right? So, Subramania, my question to you is that what is the best case for k-fold cross validation, and what is the worst case for k-fold cross validation in terms of performance? In terms of performance, what is the best and what is the worst?
In case of performance,
Performance of the execution. Performance of execution, what is the best and what is the worst? Performance of execution, what is the best and what is the worst?
it is less biased.
No, no, performance. In terms of performance, what is the best case for K and what is the worst case for K in terms of the performance part? So simple. So for the performance part, K equal to 2 is when the performance will be best. 50% of the data will be used for training and the rest 50% will be used for testing. Right? That is when, in terms of performance, right, in terms of the execution time, it will be the fastest. While K equal to N will be the worst. Right? So K equal to N is basically LOCD. So N is the number of data points. So if you're having 100 data points, I'm saying K equal to 100. So which means that at any point in time, 99 data points will be used for training, while only one data point will be used for. Understood?
Yeah, okay, got it, sir. Actually, k equal to 10 mean 2 means here the 2 will be in the testing and 3 will be in the training.
No, no. So K equal to 2 means that you are creating only two folds or two partitions. K equal to 2. Two folds or two partitions. Right? And the partitions are generally equal size. So 50% of the data will be used for training and 50% for testing. K equal to 2.
Okay.
Whereas K
But
equal
I'm
to
relating to this type of data, sir, where we have five. Uh,
no, see
uh,
for this data set. So this data set to K equal to 5. The data set that you see on the picture. So here to K data
hmm,
set K equal to 5. That's why you are having P1,
yeah,
P2, P3, P4, P5.
yes, yes, sir.
Right? But in the case where K equal to 2, what I'll do is I'll probably have two partitions. So this
Hmm,
is my partition 1 and this is my other partition.
yes,
So in one case, what I'll do is on P1, I'll use for training and P2, I'll use for testing. In the other case, I'll probably use C2 for training and C1 for testing. That's what I'm going to do, right?
Yes, yes. Yeah.
Okay, so this is the this thing k-fold cross validation, right? So generally k-fold cross validation ends up with model with a less bias and less variance compared to your LOCV. LOCV, generally the bias is low, but the variance can sometimes be very high because of this whole averaging piece. So that is the problem with this k-fold cross validation, right? Sorry, LOCV. LOCV, right? See, LOCV, the problem is that it is very binary, right? Only one data point is there. So either you have identified this one data point properly, or you have identified this one data point improperly, right? That is where the all this variability, the variance comes out. The k-fold cross validation. There's something which is called as stratified k-fold cross validation. Stratified k-fold cross validation, right? If you have studied sampling, right? So let's say this is a data point. This is my entire data set where the male is to female ratio, if I see it is, let's say 70 to 30. Now, when I'm creating random partitions, random data partitions, what might so happen is that in some data partition, right, there are only males for training and only females for testing. Can happen, isn't it? Right? In some partitions, there are only females for training, right? And males comes only in the testing part. So these things probably might end up wronging the model altogether, right? So in this particular case, what we do is that we split the data in such way that the split maintains the partitions of the different classes. So here, original data was partition 70-50. So here also, each of these partitions, they're having this 7:3 ratio. If this partition was random, what might have happened is that in some of the partitions, right, let's say that this one, right, this is the one which you're using for testing. The yellow ones are the ones which you use for testing, right? So for the testing case, let's say that in the training cases, the females didn't come up also, while in the testing cases, all the females came up. So the model has not been trained on the female cases, right? So invariably it will do a bad job, right? It might so happen in some of the cases, let's say some of the training examples are having only females, only females, and your test data is having only males, right? Then also probably the model performance will go in for a toss, right? So to take into account this kind of uncertainties, so these are uncertain cases. So to manage this kind of uncertainty, what we do is that in all the partitions, you see that we maintain the same proportion of this training versus validation in all the partitions, right? The class imbalance problem, right? Whatever is the class, that comes up equally likely in all these partitions. Make sense?
Yes, sir. It means it uh, maintains the imbalance uh,
Don't say that
across
imbalance. It
all
maintains
the
the it maintains the proportion of the target variable. The target variable is your gender, male, female. So the proportion of the target variable is maintained in all the cases. So this is this stratified k-fold cross validation, right? Understood?
yes, yes, sir.
Okay. So this is the process. So these are the advantages of this k-fold cross validation. So all the data folds you are using, so issues with irregular splits that is mitigated, right? And since each observation is used only one for validation, chances of overfitting, right, that also probably is reduced to quite some extent, right? So yeah, so balancing method, I have already told you that resample, right, do a this thing oversampling, undersampling. That is probably how you do the resampling of the piece, right? So morning, Sachin, right? Right on time, you have come. We just thought that we probably will take a break, but yeah, I will continue. Right. So we were discussing the different validation techniques where we started off with this train test, then we spoke about this the whole cross validation, right? And now, and we spoke about something called LOCV, leave one out cross validation, and then here we are doing a stratified k-fold cross validation. That is what we are doing right now, right? So just keep this thing in mind that you can always end up, you can always end up with, with a training data set. You can probably do some kind of engineering. Test data set should never be balanced. Never put yourself on the test data part. Train data is okay, not on the test data part, right? And here we have discussed this earlier, right? So one is this variance part. This is right as and when the model complexity increases, variance increases. Initially, the variance is low, but then the variance becomes high. And then on the other hand side, if you see the bias part, initially the bias is high, this becomes low, right? So ideally, right, if you see that the so this is on the training data. So training data, you'll find that as and when you increase the complexity, training error comes down and down. While if you see on the testing part, initially it comes down and then it goes up. So this particular zone, so I think around here is where it is probably lowest. So this particular zone is the part where you should try to find out your optimal. Right? As I said that you should always try to find out the sweet spot where the difference between the training and the validation performance is at the lowest. So this particular part of the error is irreducible error. However hard you might try, you will not be able to reduce the irreducible error because that comes from some inherent bias or noises in the data itself. The irreducible error you can't reduce, right? So rather what we should try to do is we should try to focus on reducing the reducible error, and in the process of reducing the the predicted error or the reducible error, we should try to do that. We should not create a overly complicated model. At the same point in time, there should not be a overly simple model, right? That is what we are going to do. So for a good machine learning workflow, what happens is that you first separate the train and test set, try some appropriate algorithms, fit the model parameters, tune the hyperparameters, right? Look into the metric and do some systematic cross validation. That is generally the thumb rule for creating your machine learning models, the workflow for a good machine learning model process. And if you remember the data which we have seen earlier, right, this is probably the optimal model, right? In the underfit case, we had just drawn a line like that, saying that it is going to be a linear model. In the overfit case, what we tried to do was this was a very zigzag kind of a case where all the data points we were trying to fit in, right? Right, which was also a very bad modeling process. While the optimal model, what it should try to do is that it should try to probably have a smooth balance in the overfit and the underfit. So see the optimal model, this is the optimal model, right? It is not that it is able to map all the cases properly. Is it that there is no bias? Yes, there are some biases. There are biases. This is a bias. This particular part is a bias. This particular part is a bias. Here you have some biases, right? But overall, right, if you look into the bias and variance part, it is balanced. It is balanced. So this is the optimal model, right? So generally, what you do is that you compare the model with the baseline performance. For a regression model, the baseline is the average value of the target variable. While for a classification model, the baseline is basically the majority, right? So that brings us to this hyperparameter part. Hyperparameter we have discussed during our decision tree classes, right? So what you need to do is that we try to do some kind of a hyperparameter tuning, and what this hyperparameter tuning will do is that it will fine tune all the model across all the available features and will try to extract the maximum out of the model, right? So rather than trying on with multiple different machine learning model and not probably having any optimal model, try doing this thing that try to have multiple models on the try to probably optimize the hyperparameters, right? And if you try to optimize the hyperparameters, so what will happen is that across one or two simple base models only, you will get the best performance, right? So grid search CV or grid search cross validation is one of the ways in which you do a hyperparameter tuning. Grid search CV, grid search cross validation. So what it does is that it extensively searches across all the hyperparameters the best combination. Say for example, if you're doing a decision tree, the hyperparameters they are the algorithm. So you can use a Gini, you can use a entropy, right? You can use a guide, you can use the classification error. Then you also look at the depth. So depth can be 1, 2, 3, all the way, let's say up to 20. The depth can be there, right? And then minimum sample split, minimum sample leap. So a combination of let's say for example, look into Gini in the Gini, right? Look at the depth of 1, minimum sample split of let's say 5, and minimum sample split of let's say 10, right? Create a model, right? See how the model is performing against your validation data. Then probably look into Gini, same Gini of 1, right? Depth of let's say 1, minimum sample split of let's say from 5 go to 10, and minimum sample leave keep it at 10, right? Boom. So like this way, you try to reevaluate all the cases, reevaluate all the cases for the model, right? Now, this grid search CV, that is what it does, right? It says the best hyperparameter set from all the pieces going in the loop, right? But the problem is that computationally extremely heavy computationally, and in the process it takes a lot amount of time. That is what happens with a grid search cross validation, right? So for roadmap of building a good machine learning process, as I said, the first part, right, people don't realize that this is the part which requires probably the maximum effort, right? You pre-process the data, do a feature extraction, scaling, select subset of the features, sampling, all that thing comes out there. And then probably spend some time on this part also, model selection, cross validation, mixed hyperparameter optimization. This one will probably take a lot amount of time, hyperparameter optimization. And then you do a evaluation. You probably keep on repeating this step until you build the best model. And once you have a stable model, you have new data, right? You do a prediction on this particular one. So this is the roadmap for building your machine learning, right? So now it's probably time for us to go into the ensemble method part, right? So, yeah, any questions with regard to this? Any question, Subramania and Sachin, for the model selection part?
No, sir.
Sachin, I think you missed out some particular part, so it's fine. Okay, wonderful. So let me probably take you now to this ensemble method, right? So sometimes people spell it as ensemble. It is not ensemble. It is pronounced as an ensemble technique. Ensemble is the pronunciation which comes out. What happens? Okay, so ensemble techniques will probably give you a brief overview, and then we'll directly so we'll take a break, and then we'll come back and complete this post the break. Okay, what exactly is this? The picture that you see on the screen. What exactly is the picture that you see on the screen? What is
One
the pic-
is st- structured.
what exactly is the picture that you see on the screen? What do you think this is? Yeah, Sachin, what do you think this is?
So can you repeat the question?
The picture which you see on the screen. What exactly this picture is about?
It looked like some hotel and buffet kind of
Yes,
thing.
exactly. So this is a buffet.
Yeah.
Exactly, that is the part. This is a buffet, right? So why restaurants have buffet? My next question. Why restaurants have a buffet system? Why restaurants have a buffet system generally?
uh,
So customers can take the their interested food
Uh-huh. So
and you know,
some people are probably interested in mainly the starters. Some people are interested in the desserts. Some people might be more towards continental dishes. Some might be interested in Chinese dishes, while some might be interested in, let's say, Mughlai or Indians. Right? See, at the end of the day, what is the objective of a restaurant? What's the objective of a restaurant? The final objective is obviously to have money, right? Profits. That's the final objective. But otherwise, this objective of making profit or money, how do you basically achieve that?
customer
Uh,
service.
Customer service, mean customer satisfaction, right?
Yes,
You want
customer
to have
satisfaction.
happy customers at the end of the day, right? If somehow your customer is not having too much liking for continental food or Chinese food, customer will probably be grumpy, right? If the customer has come in a group, so probably the customer is taking that the other continental or Chinese food, but he will be grumpy, right? Customer is not getting good starters, customers might be grumpy. Some customers only come for the love of the desserts, right? They are not getting the desserts, they might be grumpy, isn't it? Is it correct to say that? So the objective of this buffet restaurant is to make happy customers, and it doesn't know that which customer will get satisfied by what. So what it has is that so many different counters. Counter one, counter two, this particular part is let's say counter three, counter four, right? And what it knows is that the customers, they might not like all the counters, but because of this spread that they are offering, most of the counters the customers will like most of these counters, right? And probably there will be some counter of interest for the customer. So this is my interest counter, right? If that is the case, I should be able to proceed for it, right? So using this ensemble technique, right? So ensemble technique, right? It is a very powerful technique which is being used in industry by the data science experts. So like I showed you the buffet, what happens to ensemble technique is that you put your models through multiple algorithms, and the answer or the prediction for the model that comes to the hand of this multiple algorithms, right? And if you go and look into Kaggle, you'll find that majority. of the winning solution in data science. They combines this result from multiple weak models to produce the results, right? It means that most of the cases they are using some kind of a ensemble techniques, right? So also the other thing to do with ensemble is that generally when we use ensemble technique, we don't create overfit models. We generally keep ourselves to creating some simple underfit models, which means that less time is being used for creating those models, right? So see, I already told you that if you have to fine tune a model, if you have to ensure that this model is fitting correctly into all the instances, everything, you have to do a lot of checking with the model, lot of hyperparameter tuning and everything, right? So what we do out here is that since it's time consuming, we train the model on different weak learners, weak algorithms, and we basically put out the average result from them, right? That's what we try to do, right? So let me show you an example, right? So this is the example. Your task is to segregate out the pluses from the minuses. That is your task. Segregate the pluses from the minuses. So this is, let's say, your M1. This is, let's say, your M2. And this is, let's say, your M3. M1, M2, and M3. Let me put my focus on M1. So M1, if you look into the bottom part of M1, right? So my task is to segregate the pluses from the minuses. If you look into the bottom part of M1, right, this particular part, this particular region, you find that these minuses are there, right? You're happy that the minuses have been segregated out. But when you look in the top part where the pluses has to be there, you see that along with the pluses, this minus is also there. Along with this pluses, this minus is also there. That is for M1. Come to the case of M2. If I look into M2, if I look into M2, right? So this is M1, M2. So M2, below M2, all the minuses are there. These are all the minuses are there. Once again, you probably think that, okay, your problem has got solved. But no, the reality is that if you look into the above part, the pluses were supposed to be, only pluses were supposed to be there, but a lot of minuses also have come in. So M2 is also a bad model. Come to M3. So M3 probably creates another variant of this underfit model, where below the model, right, this particular part, all the minuses comes in, which is fine. All the minuses have come in this particular part. I could be very happy. But over the model, on the other side of the model, right, this particular side of the model, I would have expected only the pluses, but here also, along with the pluses, the minus comes in. So the thing is that none of the model on its own are able to solve this particular problem. And this problem is, by the way, it's not a simple problem, right? You see that this pluses, they are embedded within the minuses. Pluses are embedded within the minuses. So in that way, it is not a simple model to solve. It's a complicated piece. But if you see a combination of these models, combination of the model, what it has been able to do is that it has been able to segregate out the pluses from the minuses. The combined model, you find that it has been able to segregate out the pluses from these minuses. So this particular region that the combined model has created, this region has only the pluses, right? So that is the essence of ensemble technique. Individually, these models, they are weak models, right? But when you combine all those weak models, it finally ended up creating a very strong model for you. Right? See, for example, decision making. Since we were talking about this restaurant and this chef, right? So this chef, what he is doing is he is probably putting, right? He's trying to create a satisfied customer, right? So he has created a subsample of customers. This is sample one, sample two, sample three, sample four. He has created a subsample of customers, and he's putting the assortment in front of the customer. Some customer probably likes this assortment, some customer likes probably this assortment, some likes this assortment, some likes this assortment, and from that, right, from their preference towards the assortment, the head chef finally knows that what kind of a things he should keep in the restaurant, right? So why is ensemble, right? So typically this ensemble classifier is likely to have a lower error rate, likely to have a much lower error rate, right? In fact, the variance of the ensemble classifier that also is found to be lower than certain base learning techniques, right? So uh, let me show you to this particular case. So let's say you have three models, M1, M2, and M3. You are creating an ensemble out of those three models. An ensemble method you have created out of this three models, M1, M2, and M3. Right? An ensemble classifier is what you have used, right? Now, when will your ensemble classifier make an error? Each of these models, let's say they had a average accuracy of, let's say about, let's say 70% is the accuracy of this ensemble, right? M1's accuracy 70%, M2 is, let's say 80%, and M3 is, let's say 90%. These are the accuracies of the model, right? So, and you are using this ensemble technique. So when will this ensemble go bad? When will this entire ensemble go bad? When will this entire ensemble go bad? Yeah. When will this combined model go bad? Yeah. Some answers from both of you. When will this ensemble go bad?
So do you get the question? I mean, go back means what? I mean,
It will make a wrong prediction. When will
okay.
this?
Uh,
Okay. First, first, uh,
Actually,
first, let me ask you, right? So one of the model had a performance of 70%, right? M1. M2 had a performance of 80%, and M3 had a performance of 90%. If I create an ensemble model which combines M1, M2, and M3, what is the performance of the ensemble? What will be the performance of this ensemble technique, ensemble methods?
it should it will average all three.
Sorry?
Uh, can be the overfitting because
No, no. So my question is that you have these three models, right? M1, M2, and M3. M1 is having a 70% accuracy, M2 is having 80%, while M3 is having 90%, right? So what will the overall accuracy of this ensemble model have where M1, M2, and M3 are there? Overall accuracy of this ensemble. Overall accuracy of this ensemble technique with M1, M2, and M3.
Maybe average of these three models.
Average of this three. Okay, so what is that? What will that be?
could be 80%.
80%. So which means that the error rate is 20%. That is what you're saying. A 20% error the model will make. Since the average is 80%, it will make 20%.
Yes.
Correct? Is that correct? Is that correct to say this?
Yes, sir.
Yeah, yeah.
Okay. Yeah, Subramania, you have any point?
No, sir.
So let me put you through this argument once again. See, this particular model, right? M1, M2, M3. This model will perform badly. M1, M2, M3, this an ensemble with M1, M2, and M3 that will perform badly, right? If a majority of this model that makes an error. I repeat, if the majority of them that makes an error, that is when this model will go bad, right? If let's say only M1 makes an error, while M2 and M3 doesn't make an error, then this model will not go bad, right? Only when majority of them makes an error, it will go bad. So what is the error rate of M1? What is the error of M1? The data is given.
Mm,
What is the error of M1? How much error M1 makes?
20%.
M1, M1, M1,
30%.
30%. So M1's error is, so let's say all the three models they are giving error. So point
Mm,
3 is from M1,
mm,
point 2 is the error of M2, and point 1 error is the error of M3. All the three models gave wrong results. Or M1 and M2 gave wrong results. That can also happen. So M1 and M2 gave wrong result. Or M2 and M3 gave wrong result, which is point 0.2 into point 0.1. Or M1 and M3 gave wrong result. So only when the majority of the models they go bad, this ensemble goes bad, right? Ensemble basically takes the majority decision, correct? So here let's compute the error rate. So P into 2 is 6 into what is 1? So 6, 0.6, 0.06, this is 0.006. Okay, this is 3 to 2 is 6, so 0.06. 2 into 1 is 2.02, and 3 into 1 is 3, so 0.03. Let me add this up. So 0.06 plus 0.03 plus 0.02. So that is 0.69, 10, 11.11. And then this one is 0.006. So this one, if I add this up, 0.006 to 0.116. So the performance of the ensemble, if you see, right? As you had said that no, I mean I am just averaging out the error rate. So if I average out the error rate, the average of the error rate was 30%, 20%, and 10%. So 30, 40, 50, 60, 60 by 3 is 20% was the average. But in reality, if you see that this is the error rate, which is almost half of what you have got from average. So the ensemble will have a much lower error rate compared to each of these individual classifiers taken into account. That is the beauty of this ensemble technique. Right? In fact, the same thing I can show you mathematically also, right? So it uses something called as this binomial theorem. Right? So let's not go into the details, right? But again, you will find that if I use an ensemble, the error rate of the ensemble will be much lower compared to the base models. Right? It can be shown mathematically. So techniques or strategies for ensemble, right? There are multiple techniques, right? So one is based on how you select the models, right? Based on sample selection, how you select the sample for the ensemble, right? You can end up taking different models based on which model is being used. Homogeneous models are being used or heterogeneous models are being used, right? That also creates different kinds of ensemble, homogeneous versus heterogeneous, based on the algorithms used, right? The algorithms can be sequential kind of algorithm, right? or the algorithm can run in parallel. Create different ensemble based on the result compilation, how the results are being compiled, right? Are you averaging out the results, or you are using some kind of a voting? On that factor also, the ensemble can differ, right? And to ensemble, more than some model, it is more of some strategy. There's a strategy that you use to create a final models, right? So I'm just wondering, should we take a break right now? Can we go ahead and
Yes,
take a
sir.
small
Yes, sir.
break?
Sure, sir.
Yeah. So I think it's 12:24 in my watch, right? Let's take an 8 minutes break. Let's come back at 12:32. We'll come back at 12:32 and we'll continue on with the ensemble process. In the meantime, if you're having some questions, please put it up on the chat. Please put up on the chat, rather on the Q&A part. Please put up your questions so that I can come and answer those questions. Right? Okay. So break for this 8 minutes. Let's slowly come back, and I hope this break was useful for you. Okay, so we were discussing the different strategies for ensemble, right? So these are the different strategies, as I said, for the ensemble technique. So yeah, so let's revisit this once again. So there are many different techniques for ensemble, right? Let's focus on this one. Based on this result compilation, what does this mean? Result compilation. You can do some kind of averaging, you can do some kind of voting for the result compilation. Averaging can be simple averaging, weighted averaging. Voting can be hard voting or soft voting, right? So what does this thing exactly mean? Averaging, voting, right? Simple average, weighted average, hard, soft. What does it mean exactly, right? So let's come to the result compilation part. The averaging part is being used for your regression models, while the voting part is being used for classification models. Averaging used for regression, voting is being used for classification, right? Now then, in the averaging, you have simple average, weighted average. In the voting part also, you have hard voting, soft voting. What does it mean, right? Simple average. Simple average is pretty simple, right? So here, your model, three models are there, M1, M2, and M3. And so let's say these are probably scores, right? Let's say this particular chef, he is trying to get the rating for his food from three different people. So one is model one is model two, model three, and these are the three ratings that they have given. So he has found out the average of this three ratings. Average which came out from this is 50. Simple average. Model one, model two, model three, right? So there is no problem with this one, right? Come to the case of weighted average. In the weighted averaging cases, what this chef is saying is that, okay, I'm putting my food to three of these experts. So let's say this expert is E1, E2, and E3. But these experts also, they have some kind of a scores based on how accurate their reviews are and everything. So let's say expert 1 has a score of 0.4, expert 2 has a score of 0.3, and expert 3 has a score of 0.3. So out of 100, if I want to probably give them some kind of a weightages, these are the weightages. 40% for expert 1, 30% for expert 2, and 30% for expert 3. So expert 1 came up with a prediction of 45%, 45. Expert 2 came up with 40, and expert 3 came up with 60. So I'm just multiplying their corresponding weightages, and this is the final one which I. So that is the weighted averaging piece. My question is that what would have been the answer for simple voting, simple averaging? In this particular case, what would be the answer for simple averaging? Simple average, if you see, this is 60 plus 40 is 100 plus 45 is 145. So 145 by 3 is 3, 4, 12, 3, 14, 2. So this one will be I think will come for your simple averaging, right? It was the same value 45, 40, 65, 40. No, here it was 65 actually earlier, right? So if it was 65, that probably would give you 50, right? So here it is giving you 48.50 this particular cases, right? Simple. This is simple averaging and weighted average is giving you 48, right? Come to the case of voting. So voting basically comes into account for let's say classification problem. So for classification problem, voting comes in, and you have your this thing hard voting and soft voting, right? So in the case of voting, right, hard voting, so what we see is that the majority part. So here you have three models, right, and the classification problem. Model one is go with one, right? We classify it as this thing is one. Model two is saying no, it is zero. Model three is saying it is one. So my final prediction is one, which is the majority of this what these three models are given. So that is called hard voting. So typically, this is the process of voting which happens in the country also, right? In the country, you have a certain number of seats, right? And whoever gets the majority of the seats, so that party gets to form the government. Hard voting, and the other is basically soft voting. Soft voting. So hard voting uses nothing but a simple mode technique or a majority, right? But soft voting takes into account many other things, class probabilities, and probabilities basically are being used, right? So the class with the highest probability, that is the one that we use. Say, for example, you have three models, M1, M2, and M3, like the earlier case. So M1, M2, and M3. So if I look into the hard voting, it is 101, right? 101. If I look into the soft voting aspect, right? So M1 said 1, and for class 1, it was probably 60% confident, and for class 2, it was 40% confident. M2 was, let's say, so it said for class 0, right? M2 has, so for class 1 to 1 and 0. So for 1, M2 had only let's say 20%, and here it was 80%. While for M3, it was probably 55% for class 1 and 45% for class 2. So if I look into M1, so M1 gave 1 based on a 60% confidence. M2 gave a 0 based on a 80% confidence for class 0. And M3 gave 1 based on a 55% confidence. So if I look into the majority, so majority is 1, I say it is 1. But let's see if I look into the soft voting, where I also take into account the aggregate probabilities. Then things starts looking into the defined format. If I look into the voting aspects of M1, so this one is 5, 6, 7, 8. 8 plus 5 is 135, right? If I take the average by 3, so this is 4, 3, 5. Okay, let's look into this one. So this one is 80 plus 40, that is 120. 120 plus 40 is 165. 165 by 3, if I see, so 515, 1. If I look into the soft voting aspects, I probably can't go for model 1 this time. I probably will have to go for model 2. Because if I see the average probabilities for model 2, that is much higher compared to model 1. Have you got the idea?
Yes, sir.
Yes.
Wonderful. So this was the hard voting and the soft voting. And then the question comes in that how can you improve your ensemble, right? Many different ways to do that. One is you can look into the difference in the population size, difference in the initial hypothesis, difference in the techniques that you are using, and difference in the initial seed that you are being using. So all these things could be used to improve your ensemble technique, right? Difference in population, difference in hypothesis, difference in technique, difference in the initial seed, right? So at the end of the day, right? Let me talk about your ensemble. So my question to you is that what was the characteristics of the ensemble model which we are talking about? Characteristics of the ensemble model which we were talking about. Characteristics of the ensemble model which we were talking about. Yeah, anyone? Characteristics of the ensemble model?
Characteristics, sir,
Yeah, characteristics.
is combination of multiple models.
Combination of multiple models, that is fine, right? That is the principle, but what was the characteristics of the underlying model, let's say? Underlying model, I'll just help you. Underlying models are typically your underfit models.
Yes,
Underfit model, what is the characteristic? They will have a high bias,
yes,
right? But low variance.
low variance.
Right? So let's look into this one. So let's partition this particular piece into all this multi. So let's say this is M1, right? This is the M2 and this is M3. So M1, right, you'll find that, okay, this is probably where the predictions are coming in. M2, let's say this is M2, this is where probably all the predictions, let me use a blue one. M2, this is probably all the places where these predictions are coming in. See, all are weak models, by the way. M3, let's say this is all the places where these predictions is coming out. M4, if I see, these are all where the predictions are coming out. M5, let's say these are all the places where the predictions are coming out. So if I look into this individually they are underfit models and they are giving a bad performance. But overall, right, if I look into the models, right, the overall models, right, the overall ensemble, right, if I average out their performances, I am very close to my original estimate. I'm very close to my original estimate if I average out the model performances, right? Also, the other thing is that all these models, they had a high bias and probably a low variance, right? So when I take the ensemble part, overall, I'm able to reduce the bias part and the variance part also, right? Though it doesn't remain as low like this, right? So these are probably the parts where the variance is very, very low. It doesn't remain this low, but yes, right? We are able to improve on the variance part of the model as well. Right? It is not that low like a underfit model, but again, still it is at a decent level, right? So it might so happen, say for example, you are trying to do a classification problem, right? You are trying to do a classification problem, and let's say these are the classes, right? You have predicted, right? So 1, 0, and actual 1, 0. So let's say 100 data points you are having, right? So this one is having 30, and this one is having let's say 40, right? So which means that here 70. So let's say 20 have come here and 10 have here, right? In both the cases, the actual were 50-50, right? But your predictions were pretty way off, right? So here, this one is the false positive, and this one is the false negative which you have out there, right? And the problem with base learners individual model is that you try to improve on the false positive, the false negative probably gets impacted, and vice versa. Now, for an ensemble, what you can probably try to do is that you can try to focus on, let's say, models which probably improve on one particular aspect. So let's say once again, this is 1, 0, 1, 0. Same, this is predicted and this is actual. So let's say that I try to reduce the false positive, right? So false positives, if I try to reduce, so false positives are basically instances of actual negative, right? False positives, right? If I say that this is the actual case, and this is the predicted one. So predicted, so this one is, so my bad. So this is your false positive, and this is 0. This is your false negative. So these cases are these false positive case. So in actually these are the 0, but you are predicting them as a one false positive. So false positive ideally should come more and more in the domain of this things. This my bad. Just a moment. False. Yeah, these are false positives, and these are false negatives. Yeah. So here, if I look into this false negatives, so false negatives, if you see, right? So I am predicting them as negative, but they are actually positive. So false negatives should try to move out here, whereas false positives should ideally try to move in here. And let's say that after some changes, what I've been able to do is that I've been able to decrease the false negative cases. So which means that earlier my this 30 was there. Now it has become, let's say, 45, and only 5 false negatives I have. So I've been able to improve on the performance of the part to do with this one. But on this particular side, right, on the hindsight, what has happened is here this part was changed. So false negatives I'm able to reduce, but false positives increase. So this is your model one. Let's say you have another one, which is your model two. So where my focus is more on, so this is your actual, this is your predicted. So here my focus is more on reducing the false negatives, right? So initially my false negatives were 10, right? Now I had done a reduction. So my false negatives this time came out as 5. This is, let's say, 45. Just a moment. This is, let's say, 45 this time. Okay. Just a moment. Yeah, my bad. Just a moment. Oh, this slide has stopped. Just a moment. I have to just restart the slide sharing. Just a moment. It's taking some time. You know the problem? The all the data which I have put up, the data was probably on that one. Anyway, too much. Okay, so here was my initial model, right? Let me put in quickly my original model. So 1001. So let's say this had 30, this had 30. Both of them, let's say they have 2020, right? So this is my predicted, and this is actual, right? So so predicted. So this is my false positive. This is my false negative. Now I've probably used an ensemble, a very simple ensemble, which focuses more on the positive classes, right? So in the case, what happened was that if it focuses more on the positive classes, right? So then all the cases which were incorrectly identified as these negative cases, which is these cases incorrectly identified as negative, right? So now it comes in the positive class. So let's say my positive class right now becomes 45. This is 5. But the problem is that so false negatives, they have been reduced, but a false positive, right, they get increased. So from 20, right, right now my false positives, let's say they become 30, and this becomes 20. Or I'll keep it simple. I'll probably for T and same. I'll keep it in this way. So this is what has happened, right? In my M1. Let's come to my M2. For the M2 case, right, what had happened was that this time my focus is more on the class 0, right? So on the class 0, if I focus more, 1, 0, if I focus this time, so this time what I've been able to do is this I've been able to reduce, right? But on the hindsight, what happened was this change. And then you already had this one, right? So you say that if I try to look into the one class, right, then the other class suffers, right? But again, if I look into the ensemble right, if I take a voting of this M1, M2, and let's say this is MN, right? If I take a voting of all those, then you'll find that in most of the cases, I'm able to identify the positive classes from the negative classes. The negative class is also correctly identified. The positive class is also correctly identified. That is what will happen for the case of this ensemble, right? And I think I've shown you this particular diagram. So here you have more partitions of the data you have, right? And you try to look into it, right? So homogeneous ensemble is the most common type of ensemble that you're having, and it uses the same base learners for the model. And if it uses the same base learner, what happens is that the model is homogeneous, but this underlying data, it is sampled into this different subsets. That is what happens with a homogeneous ensemble, which is the most common type of ensemble, right? So bootstrapping, that is basically a statistical technique where you create multiple samples of identical size from an initial data set. Multiple samples of identical size from an initial data set, that's what we do with the bootstrapping, right? And this subset which you create from the original data, they are of the same dimension that you do, right? And these samples are created by instances drawn with replacement. So let me show you that the example. So this is your data point. And what you're doing is that from these 12 data points, you are creating bootstrap samples of size 5. So you see, first sample, 1, 10, 3, 8, 3. So this 3 has come up twice. Next, this one, 5, 4, 2, 11, 9, 3. Right? Like this, I create multiple samples. Last one, you see 5, 12, 1, 5, 6. 5, 12, 1, 5, 6. Right? 5 have appeared twice because it is a sampling with a replacement. That is what I do to create this bootstrap samples. So bagging, right? This is a like one of the most uh, used techniques for your ensemble. Bagging stands for bootstrap aggregation. I'll repeat: bootstrap aggregation. That is bagging, bootstrap aggregation. So what happens in a bagging technique or the bootstrap aggregation technique is that first I create the bootstrap samples, right? So which is sampling with replacement of identical sizes, right? So out here, it might so happen that some of the data points are not considered. Say, for example, right here only we can see 3 samples created. I don't see 7 coming out. 10 is there, 11 is there, 12 is there, 9 is also there, 8 is there, 7 is not there, 6 is there, 5 is there, 4, is it 4 is there? Yeah, 4 is there, 3 is there, 2 is there, 1 is there, right? So in this bootstrap sample, I see that the 7, at least in these 3 examples, I have not seen. It might be there in some other examples, it might be. So there is a small chance that all the data points might not be considered, right? So that is a possibility, right? So these are the statistical properties drawn from independent and identically distributed data set, right? And the initial size of the data set, that should be large enough so that you can capture the underlying complexity of the distribution, right? That is what you could do. and each of the samples they are independent of each other, right? So that they are also not much correlated, right? So bagging, which is basically bootstrap aggregation. So first is that you create these bootstrap samples. Bootstrap aggregation. First, you create these bootstrap samples, right? So original data. From here, you create subset 1, subset 2, subset 3, subset 4, subset 5, right? You create these bootstrap samples. And then on the subsets, you fit your model. So model 1, model 2, model 3, model 4, model 5, right? And then you combine the prediction, right? So if it's a regression problem, you do a simple averaging or a weighted averaging. If it's a classification problem, you do a simple voting, soft voting or a hard voting, right? And typically what happens is that for a tagging process, generally these models are the same kind of models. So one of the classic examples of bagging is that of a random forest. So in random forest, what happens is that you create all these random subsets of the data. You create all this random subset from the original data you create, and then you fit this multiple models: model 1, model 2, model 3, model 4, model 5. You fit on this subset of the data, and then you probably combine this on the predicted part. Random forest, right? So these are the properties that the bootstrap aggregation creates sample with replacement from our training data. That's what it does. All feature selection have the same property and uses homogeneous weak learners independently, right? So it's a parallel algorithm. This bagging, it's a parallel algorithm. So first you select the samples, and then on the samples in parallel you create multiple algorithms, right? So this data selection and model building process works in parallel and combines to a majority voting classification and uses averages in regression. That is the bootstrapping aggregation process, bagging, right? So this is the process, right? Samples are created. You fit the base learners on these samples, right? And then you have this models, and then probably you take a voting or you take a averaging from this models, right? So bagging process, bootstrap aggregation, homogeneous learners, right? And you use a base classifier, and it's a parallel algorithm. So these are the properties of this bagging process, right? So one of the examples, as I said, is that of a bagged decision tree. Each tree is having its own data sample, and the prediction will be based on aggregating the p value, right? So this is the bagging process, random forest, right? As I said that multiple decision trees will get created, and your final process will probably average out all this different decision, right? So random forest, it follows this particular piece, right? So I'll quickly take you to the the process of boosting, right? Because at least if you know ensemble, bagging and boosting, all those things you should be knowing properly. So generally for your this thing random forest, these are some of the hyperparameters that you try to do. Max features, maximum number of features, number of estimators, minimum sample leaf. These are some of the things that you use in the case of this random forest. Maximum features, number of estimators, minimum sample leaf, right? And then comes to a boosting, right? Boosting, as I said, boosting, by the way, it is a sequential technique. It's a sequential technique. So bagging was a parallel process. Boosting, by the way, it's a sequential technique. So in which what you do is that these algorithms, they are trained on the entire data set, right? And then the subsequent algorithms are built by fitting the on the residuals, or basically on whatever is the leftover from the first algorithm. And typically what it does is that it gives a higher weightage to those observations that were poorly predicted. It gives higher weight to those observations that were poorly predicted, right? And in the process, right, what it will do is, as I said, that it will use the multiple weak learners. It will use multiple weak learners, right, which might not be good for the entire data, but it's good for some parts of the data set. Right? So each of the model, it basically boosts the performance of the ensemble. Right? Let me show you an example. See this one. Right? So these are my multiple data partitions. This one is correctly identified, incorrectly identified, incorrectly identified, correctly identified. So this is my first model which I have created. Right? Now, the thing is that the ones which where I have correctly identified, I'm happy. I'm happy for those processes. But the ones which have been incorrectly identified, that is probably where I should put my focus on those. So what I do is that for this one, so this is P1, P2, P3, and P4. The data points, it can be data points, it can be data partitions of the same characteristics. So P1, because it was probably identified properly, P1 weightage comes down. P2 weightage goes up. P3 weightage goes up. P4 weightage comes down. So this is the new P1, P2, P3, and P4. So more and more samples from P2 has come in, P2 and P3 has come in because they were not currently identified, and lesser samples from P1 and P4, they have been taken this time because they were correctly identified last time. So now after this, when I try to fit in the key, right, what I see is that this one correctly identified, correctly identified, correctly identified, but this one incorrectly identified. So this one goes down, goes down, goes down. This weightage goes up. So this time, this is my P1 smaller, P2 smaller, P3 smaller, P4 larger. This time, P4 kind of data I've been able to identify properly. P2 I've been able to identify properly, but P1 and P3 has gone back once again. So this time P1 will go up, P2 will come down, P3 will go up, P4 will come down. So now this is where P1, P2, P3, so after a certain point in time, I find that all the cases, they have been correctly identified. So this is the process of boosting, right? So one of the process of boosting, as I said, it's a sequential technique, right? And it adjusts the weight of the observation based on the last classification. The weights gets adjusted based on the last classification. And then if the observation was correctly classified, it will try to decrease its weight. If it was incorrectly classified, it will try to increase the weight, and vice versa, right? And in successive iterations in the booking process, we will strengthen all the weak learners to get a strong learner. We strengthen all the weak learners to get a strong learner. And what happens that boosting in general, it will decrease the bias error and it will build a strong predictive model in the process, right? But on the pitfall, it does have a chance to overfit the training data. So here is probably the last piece which I'll show for the day, right? I know I'm coming between you and your lunch. So this is my original data set, right? And I have to separate the pluses from the minuses, right? It's not an easy problem. It's not an easy problem if you see that this decision boundary, if I see decision boundary is pretty difficult. In fact, this, This is probably how the decision boundary should look like. I think you can actually say that, sir, it will probably create some kind of a overfit model, right? If you try to do that. And that actually happens sometimes in the boosting technique. So first, this is my base classifier. Simple model. Simple model I have created. So where these are the minuses, these are the pluses. So you can find that this particular region, it will keep separate on the minuses from the pluses, but this one is incorrectly classified. These two are incorrectly classified. So the next iteration, what I'm going to do is I'm going to increase their weightages, right? So this one weightage gets increased. This 2 point weightage gets increased. Once again, I fit a weak learner on this. So weak learner, right? This is a weak learner. On this side of the weak learner, the negatives are there. But on this side, both the positives as well as the negatives are there. So where I was expecting only the positives, the negatives also have come in. So this one, and this one incorrectly identified. So whatever were correctly identified, their weightages comes down. Whatever was incorrectly identified, their weightages goes up. So this one comes down, this one comes down, comes down, comes down, comes down, comes down. This one also comes down, while this, and this weightage goes up. And then the ensemble which I create once again, right? This is the ensemble, right? This once again have been able to identify the pluses probably, but in the minuses part, a lot of pluses have come in. So in the next iteration, what will happen is probably that this one, and this one, their weightage will go up, right? So this model is adapting and boosting the performance. And finally, this is probably the classifier which I get by combining all the weak learners. I combine all the weak learners, and you see how this combination happens, right? I'll illustrate how this combination happens, right? Let me partition this whole part into multiple spaces, right? Let's say this one, this one, this one, or let me just, sorry. So let's say this is a partition, this is another partition, this is a partition, and let's say this is another partition, right? So let me make those partitions P1, P2, P3, P4, P5, P6, P7, P8, P9. There are 9 partitions which are created. Let's talk about P1 partition. If you see the models, right? These are the 3 models which I have: M1, M2, M3. So P1, should it be blue or red based on the majority voting? Quickly, I think both of you are there. Just quickly give the answer. P1, should it be blue or red? Yeah, Sachin, Subramania.
P1 is blue, sir.
P1 is blue. Very good. P2, should be blue or red? P2, should it be blue or red based on M1, M2, and M3 majority voting?
Uh, P2 is also blue.
Blue. P3,
P3 blue.
very good. P4,
P4 is also blue.
P5,
P5 is red.
right, very good. P6,
P6 is plus red.
very good. P7,
P7 P7 actually can be
see this
minus.
particular part, majority,
It's red.
red. This one, I think this one was
Red.
this once again red, and
Yes,
this one.
red and red.
So if I draw my decision boundary, right? Thanks for pointing out. So I have to segregate the reds from the blues. So this one, and this one. Here also you see this one. So the blues to the reds, they have been perfectly segregated. Add a boost, adaptive boosting. Got the idea?
Yes, sir.
Okay, so this is the steps, all the observations, equal weightages. Then a model is being built on this subset of the data, right? And then what happens is that we calculate the errors, and the ones which were incorrectly classified, we try to give them higher weightage for the next observation, and we try to do it till the time there are no errors which are there, right? So advantages is that can be used with several different classifiers, improve the classification accuracy, commonly used, simple to implement, right? And though they say that it tries to fit every point, it doesn't overfit individually, but fairly good generalization happens with adaptation, right? So with this, let me close this particular session, right? So for your exams, right? Again, whatever we have covered, those things probably you can expect in the exams to come more and more often. I've already shared the slides, right? In the exams, you'll not be having any kind of hands-on coming up, right? So you can be clear on that particular part, right? You're not going to have any kind of a hands-on for the this thing, right? But otherwise, try to look into the theoretical aspects, right? More properly, and yeah. So I expect that you will do well in the exams, right? Right. So all the best for your exams, and this is my last session with you. So machine learning 3, I'll probably will not be coming back. There will be some other faculty who will be taking up the machine learning 3. Nevertheless, it was wonderful being in touch with all of you, right? And I wishing you all the very best for Diwali, right? So here I'm just going to share my this thing. So I'm not very regular on this thing, but if you want to connect with me on LinkedIn, yeah, you can probably connect with me. This is my LinkedIn handle, Sahasola, right? So great meeting you guys, right? I hope whatever we discussed, it was interesting and you learned something from it, right? That was the main motive. So yeah, wishing you a very happy Diwali to you and your family, and all the best for the upcoming exams. Only request is please write to the point, right? Don't write verbose or irrelevant stuffs, right? Writing verbose or irrelevant stuff doesn't mean that you will get better marks, right? To write to the point, small, crisp answers. You guys are already working people, working folks, right? Again, I mean, it should not be too much of a challenge, I think, at least for you guys to answer. That is what I believe. So, yeah, right. That's it from my side. Please go through the async content as well as my slides properly. I think that will cover most of the pieces. I think between Sachin and Subramania, right? Sachin missed some of the classes. Subramania, you also missed probably some of the classes. If possible, go to the recordings, right? I have tried to make your learning as lucid as possible, right? And I hope you all do very well. Thank you all. Take
Thank you,
care,
sir.
right? Nice speaking all of you. Take care.
Thank you, sir. Thank you very much. Happy Deepavali.
Happy Diwali to you and your family. Take care. Bye.
Thank